Ladies and gentlemen, it's a great pleasure for me to give here a talk on the EXPO 2024 in Nanjing in China. It's a pity that I cannot be physically there at this conference, but maybe next year that is possible. Ladies and gentlemen, my name is Georg Ostermeyer, and I would like to talk today a little bit on data science, analyzing brake measurement data with data science. Here you see my agenda. After a short introduction, I will go to measurement data usually you have in your company, then go to the methods of data science. Introduction will take care a little bit on two technical terms which are misused in the last time a little bit. So I would like to give a short definition on what is a tribal system and what is a model. A tribal system is a technical system where friction is an essential part of the functionality of the system. Such a tribal system has a classical structure of the life cycle. It has usually three parts. The first part is a running in process of this system. This running in process defines in a very, very eminent way the lifetime of such a tribal system. Then the next part of this life cycle is the working time. That is usually that time you are using this technical system. And the third and last part of the lifetime, that is a failure time. That can be a very, very short time interval, but it can too be a very long time interval. Usually you are dealing with the system during the working time. And a very, very famous example of that is a combustion engine. Here you have the, let me say, friction surface between the cylinder head and the cylinder bore. And of course, brake systems are such tribal systems too. But let me come back to the combustion engine. When I buy my first car, I had to do this running in process of the car for my own. That means the first 500 kilometers I was not allowed to drive more than, I don't know, 50 kilometers per hour. Then the next 2000 kilometers I was not allowed to drive more than 70 kilometers per hour. And that all only just to have an, let me say, optimal running in process to guarantee that the lifetime of the motor is rather large. And because that was, of course, very, very difficult, and not everybody was very good in this running in process. The OEMs started to analyze that, and they found really a solution in that. They found out that the surface finishing is essential, and the running in process nothing doing than, let me say, nanocrystalline structure of the material in the inside of the cylinder bore, embedded a little bit additives from the oil which is used. And doing that, they could guarantee a rather long lifetime, which is independent of the misuse of the customers. Of course, the lifetime of this system is defined too by the usage, by the maintenance, and by the aging. But whatever there is, the modeling of such a system is always concentrating on the lifetime, on the working time of such a tribal system. But let me come back to the brake system. Again, the brake system is a very famous classical tribal system. There is this brake, classical tribal system brake, a very complex material system. We have very different friction partners. We have very high friction power in the system, and we have wear in the system, essentially changing this system. And so it is absolutely unknown what is the real running in procedure for brakes. Of course, you know some bedding applications you are using, which is doing something like that. You have rotor coating. Coating seems to be a good idea because that is usually one part of the running process of classical tribal systems, and that is the reason why rotor coatings usually have a very, very good impact on friction in brakes. The usage. The influence of usage is now nearly unknown. We have changing in the usage by the new mobility, moving from combustion engine to electrical engines. There are coming up emission constraints, which is going into the mobility of this brake systems. And we have maintenance questions. What is humidity doing with brake pad? There are just in the last years coming up a lot of papers dealing with that question. It is not solved yet. And then we have aging. We have chemical reactions in this brake pad which are not understood when you have a long usage time. And of course we have change in the geometry by wear, and that can change the NVH behavior, for instance, such brakes. So all of these points we have in brakes in this classical tribal systems are unknown. So the next question I want to focus on is, what is a model? You see here on the right side the world, and when we have a special point where we want to put questions on the world, usually we take a clipping region. And this clipping region produces such a box where we have selected input data and selected output data, and in between copy of this clipping region, a model. And usually this model is a simplified substitute of this clipping region in the world. And the idea is just to replace questions to the world by questions to the model. And there are very different realizations of this substitute. Human intelligence, this is rather old, but you can have purely hardware realization that are, for instance, systems, chassis dyno, inertia dyno, scale test, or whatever you are using hardware, that can be abstract models, abstract descriptions, as known from mathematics or physics. And there can be hybrid models which are partially hardware, partially abstract. Very famous name in this is hardware-in-the-loop simulation coming up in the last years. Very simple speaking, usually you use something like this. When you have a system where that part you have understand, you can put in an abstract model, and that part you have not understand, you can put in a hardware model. These models can be very, very complex, especially the mathematical and physical models can be linear, nonlinear. You all know these classifications we have. But whatever the model is, the idea is to get a twin, and when it's an abstract model, to get a digital twin of this substitute of this clipping region of the world. You all know very, very famous examples for that. You are using that when you are computing complex eigenvalue analysis, or you are computing NVH issues of your brake, and there are a lot of other, let me say, digital twins. One special digital twin I would like to show you on the next slides. It is a digital twin for brake pad material. It is a friction material representation in a unit cube. And this unit cube of about 3 millimeters times 3 millimeters times 3 millimeters consists of very, very small cubes of size 5 microns times 5 microns times 5 microns. And we have here different materials these elementary cubes are, phenolic resin, metal fibers, and so on, air pore. And we have here a correct reproduction of the volume and the size ratios of all these materials. We have a creation of a center point symmetry. That is a mathematical constraint just to get answers for material which is much larger than this part here. And as a result, we get rather good reproducible simulation for material comparisons. And that is the starting point for thermal studies we did 12 years ago. Here you see a very simple example. The brake disc is coming down to the upper face of this cube. You see just at the beginning of the brake operation, the disc surface, heats the brake pad, and then the heat is running into the brake pad because of this very, very different thermal behavior of the materials we have the brake pad. And at nearly the end of the brake, the disc is cooling down the surface because the disc gets much quicker cool than the brake pad. So we have in the brake pad something like a heat wave which is running through the pad rather slow. By such heat dynamics, we can then look, for instance, for the oxidation of cokes. That means when we have at a special point inside the brake pad a special temperature, and there we have in a direct neighborhood coke and air, then oxidation is possible. And what we can see here is something like a dynamic observation of that. There was coming up in the last years a lot of papers which are dealing with posthum detection of these things. This is possibility to do that online. Another question Mr. Bode had computed here is the pyrolysis of phenolic resin. These rules you can get here from reaction cards which show when there is a special temperature, then this phenolic resin is going in that and that constitution, that direction. Last but not least, we are just reactivating these models and start to question what is humidity doing with brake pads, because that is very actual question and there is no answer yet. And we believe that we have here the possibility to understand some of these effects humidity is doing with the brake pad. When you look at the realizations of this substitute, then the hardware, hybrid, and the abstract models have another property. They produce a huge amount of data. And to handle these data, there's coming up a new word that is big data. And the science taking care for that is data science. It's looking not only for handling big data, but too for understanding the, let me say, structure of these data and the information which are in these data sets. Besides data science, the nomination of artificial intelligence is coming up. And with those, again, twins and digital twins should be generated. AI is a very, very famous word. And I would like to go a little bit more in detail to the history of AI and then go to the data. Artificial intelligence is surprisingly very, very old. Each culture has its roots, like golem or homunculus, where they are thinking on artificial intelligence, artificial human beings. And this is in nearly every culture to be found. But the start point is, I think, a paper from Turing on machine intelligence. Turing did unbelievable fine work on question that you can deal nearly everything, every problem with digital systems. And in '56, AI was even founded as an academic discipline, the first time, I think, in America. And but that was not very successful. It was the first wave coming up, but the computer power was very less. The algorithm was nearly unknown, and so this first wave goes down, and we got a first AI winter. Some years later, we got in the second wave expert systems. Expert systems was rule-based systems, something like if then else. and working on huge databases, they were in some areas very, very successful. For instance, in geologic explorations, but they were not very successful in very, very other fields. One area of application was the substitution of compounders in the brake industry. And to my knowledge, there was no system which was really successful because also of the cost of the IT system and the experts for the IT system was nearly the same than that what the component was. So there was a second AI winter coming up with these expert systems. But then there was coming up a third wave, which is living just today. That is pattern recognition, recognizing AI systems. The keywords for that is deep neural networks and deep learning, reinforced learning, data-driven modeling, and these pattern recognition is possible in all data sets, not only graphic data, it is possible in measurement data, it's possible in language data, it is possible in social data, whatever you want. And there is one point which is very, very essential, that you can make these systems self-learning. Whether the human brain is too a neural network as far as we know, there are huge differences between human intelligence and artificial intelligence. By the human beings, we have cognitive function, we have knowledge expert. The artificial intelligence only mimic human-like cognitive functions. And one point may be that human intelligence has many, many filters for analyzing data that are ethic filters, cultural, religious, educational filters. AI has no filters a priori. The advantage is, of course, to find new patterns in data sets which you may not see as human being. But the problem, of course, is the correctness of data, because small noisy data can change the pattern the AI is recognizing totally. So data with hidden defects or can be very, very dangerous for AI-driven systems. Because AI are not knowledge-based expert, even the very, very famous generative AI ChatGPT is a language-based expert, not a knowledge-based expert. The question comes up, is it possible to couple physical a priori knowledge with AI, that is something like knowledge constrained AI, knowledge informed AI, and new neural networks like Gaussian networks with these constraints, just to get more robustness against data uncertainty and data leaks. And there are many, many methods just dealing with this question, and I want to come back to that and deal with physical backbone models, which are, let me say, something like the physical backbone of an AI, just to be or to get this robustness against data uncertainty. Let me shortly come to measurement data of brakes. Everybody of you had these data in the company. I will very shortly look on boundary layer models and then come to physical backbone models, the principle of physical backbone models. On the left side, you see one form of data, measurement data, that is Akamasa test. The blue lines you can see here is the friction coefficient in these brake operations. And when you're looking at that, you can see that it is not possible to explain the brake friction by Coulomb-like models. Coulomb said that it is more or less a constant you have here. So very early there starts to get coming up new friction models. For instance, Dahl model and so on. I did it too, especially for brakes. It was a second order differential equation. And the idea behind this model can be seen here. The surface topography of a brake pad is rather complex. And the idea is that wear particles moving through these contact zones can form temporary additional contact areas between brake pad and brake disc, which modulates the actual friction, which can get a little bit more larger or smaller. So the friction coefficient is breathing with this wear dynamics in the boundary layer. The principal functionality of that can be seen here. We have input power, and the input power produces wear and heat. The wear produces wear particles. The wear particles, together with the heat, produces these additional contact patches, which makes the friction coefficient a little bit larger. On the other side, we have corrosion effects by wear, which will limit the lifetime of these additional contact patches. So when we're looking at the friction, the idea is very near to look for the equilibrium of flow of the friction coefficient instead of the friction coefficient itself. So we have functions which want to move up the friction coefficient and other effects which want to lower the friction coefficient. And when you are writing it down, then you came to this friction model. It's a differential equation of second order, which can describe this friction of brakes rather well. We have simulated this idea of this boundary layer dynamics, and we've confirmed the dynamics of patch and non-patch geometry of such a brake pad. And we can confirm the topography, and we can confirm the wear in principle, and we can confirm the heat distribution we have in this brake pads. And what we found out, that this patch dynamic is a very, very general effect of a stable and robust self-organization process on friction surface, not only brakes. That is, for instance, hip joints. You have such a film which has such patch, not patch structure, which is dynamically changing. When you're looking at rail-wheel contact, you find on the rails wide layers which are something like these patches which are breathing here on the rail. And this was a key just to understand a little bit more on that, what in brakes is possible. So taking into account the dynamics of this patch geometry dynamics, then we have an explanation for the variation of mu during the braking history. And when we go down with the time scale and look in a very short time scale on these patches, then the patch geometry is frozen, but the patch are lying on a soft polymer matrix and can move tangentially. And these vibrations are very high frequency vibrations, and there can be synchronization effects, making something like a really strong wave which is running through the brake pad, and that can explain even NVH phenomena, and that was starting point for many, many other research in these topics. Of course, the main question is how we get the parameters of these differential equation set. There was a very famous work, best paper in that oral bike from Wang and others. He has a very, very nice method to get these parameters and to deal with these equations. And then 1 year later, there was a very nice paper by Falpe and me at the SAE conference in USA. Mr. Falpe found out that you has used 4 areas in the pressure velocity diagram for which you have used a own set of parameters for this differential equation. Then we're able to describe the friction of brakes very, very well. Here you can see some results he found out. There was a very, very good approximation of kappa free and pads with low content of kappa. I will not go in detail. That was rather nice. But of course, when we want to have a backbone model of a brake, we not need only the friction coefficient or an approximation of the friction coefficient, we need a model for the total brake system. Let us look how to do that. Here you see my friction law with some parameters. Some of these parameters are coming from the brake operation, for instance, the normal load and the velocity. Other parameters is essential for the time coefficient or time properties of these values we are describing here. A very essential part of the brake is, of course, a brake disc, especially with respect to the heat properties of the total brake system. And when we introduce a brake disc temperature, you see then the mu value equation is changing a little bit. But we can do much more. You can see here an additional equation of film stream, because we know that the brake pad leaves a film on the disc, and it has something to do with wear, it has something to do with it properties of the friction, and there are very nice papers dealing with the structure of this equation in 2002. And even with this model, we are able to simulate large part, nearly every part of the Akamasa test. Here you see, for instance, two different materials, rather good approximation we got. And even the SAE 2521 test can be simulated rather well. You see here the black crosses, that are the measurement data. The red line is simulation. Please think of that this brake model has to be simulated too in this time intervals where no brake operation is, because you need this time just to cool down the disc. But of course, you can refine this model in many ways. One thing is, for instance, this film the brake pad is producing is lying on the disc and then running on the disc back to the pad again. So we have something like an input and an output of this file stream by the brake pad, and we have information how that what is coming out of the brake pad is running in the brake pad again after one round on the disc. So in this very simple form, you see it here, the film stream in the brake disc. It is describing only wear. Theta 4 is something like wear constant, Eichert's constant, we can use here in this form. But in this form, it is a rather simple approximation of the brake, because that what we have here is a pad model is a one-point contact, and we know that the brake pad, of course, is a summation of many points or many contacts we have. On the other side, on the brake disc, we can put a lot of more intelligence in the equations. For instance, using transport equations, how this film is changing from the output of the brake pad to the input of the brake pad again. It's temperature dependent, velocity dependent, and so on. And so we can deal here even with a question on emission behavior of the brake pad, the brake system. But whatever you do, how much more complicated we do this model, we get really a huge problem, because we get so many parameters in the model that the question is where we get these parameters. And a model where you cannot identify the parameters is absolutely useless. So the question is how we can find the parameters even when there are many parameters in our model. And the next question, of course, is when we have such a backbone model, then we have a physical model in mind. And the question is it possible to ask the data set, say, is there an explanation for another physical model inside that? So is it possible to get more information on the physical processes we have here described by this data set we have? This is, of course, start point for data science here in this talk. So I will look at the parameterization of physical models, and the next step, the question, is it possible and how to do the detection of new models in the data sets. Here you see a very famous, well-known situation. We have data points that are the blue points on the left side, and what we want to find is something like a regression line. The regression line is a very, very simple model for explaining these data. Of course, there are some differences. The data are not so ideal than this, or as this line says, but this line would be a help just to explain the direction of these points and the idea within that. So the question is how we can get such a regression. Of course, there are many methods to do that. One simple method I will use in all these slides in this talk is given here. So with each of these pairs, y and x, we can formulate these linear equations. And all these equations have two constants. It's m and c. And what I'm looking now is I will look at all these equations and I look for those parameters m and c so that the distance of this red line to these points here is in any sense rather small. That is formulated here. I'm sorry for that formula. It is something like a least square solution. And how to do that? You can put these equations in such a linear system of equations. And you see you have on the left side y1, y2, and so on. And on the right side, you have this matrix with x1, x2, and then 1 in the column. Then we have here a vector m and c. That are the both variables which are unknown. What we have to do is just to solve this equation, or just to solve the system of equations. And because that is not, of course, a quadratic matrix, there is not a unique solution. What we need is a least square solver. That is a solver which can solve these equations. It doesn't matter how many equations there are, we at every time get a solution with the least square solver. And when you use such a least square solver, then you get two parameters, m and c, a solution for them. And when you are looking for the equation, then you can see here this red line, which is given by these parameters. Of course, we can use it to analyze complex data, more complex data systems. You see here cost of living space over size. I think it's New York, but it doesn't matter. And we can use this system of equations just to solve it with respect to m and c, and then we get a model, a linear model, where we can try to explain the system. But we have not only, or we have y and x, and what we can do is to compute with x the x square. And so what we can do is we can put one more column in this matrix, and you see then we solve this system not only for two parameters but for three parameters. And now we can compute this and compute the parameters of this quadratic equation. So we have a new model, a quadratic model explaining these parameters. In this special case, there's nearly no difference between the linear or the quadratic model. So we have seen that we can parameterize a simple system by a linear line or by a polynomial. But the question is, of course, when we have such a physical model, as we have seen it in the slides before, we have differential equations. And can we identify the parameters of a differential equation with these methods? And here you see a set of data, yi over ti, and that is from a PT1 controller And what you can expect when you see here is, of course, such a linear differential equation. And the question is, can we use such a system of equations to get the parameters a and b by the data sets yi and ti? And of course we can do it. The only problem we have is that we have to compute yi dot. So the question is how we get a rather smooth yi dot from the measurement data. You see here these data, these noisy data, and but there are several possibilities to do. I've taken here the Savitsky-Goulai filter, which is a filter with the behavior of something like a smoothing moving mean value method for the data yi and ti, and it is possible to get a rather nice, simple first derivation of these data. And with that, you see here on the left side, the red lines, that is the filtered values and the derivation of these values. And when we put that into this system of equations, then we can compute these parameters a and b. And when we now take this differential equations with these computed parameters a and b, then you can see that we get a very famous approximation of these values we have here in this data set. So what we have got here is a parameterization of the differential equation of a physical model. Of course, when we're looking at the brake system, we have a much more complex model. You see here only the first equation in black, mu dot, and we have then a matrix which contains the measurement data and other input data like the velocity, nominal, the mu value. And we have then this vector compute containing the parameters of the differential equations, what we get there. And we have seen that this system is always solvable by a least square solver. But what we can do now is just to ask, is it possible to ask for the physics in this model? The idea is very simple. You see here this system we had just on the slide before, and when you are introducing here a new column, for instance, v square with v square, we at the time point ty we have. So v square is only a numerical computation from the measurement data in a very simple way. We could put this additional column inside. Then, of course, our vector we want to compute c has to get another component, and then we can compute that, and we can ask for the parameters we have for v square in our measurement data. Just to see how to do that and what problems may occur and how to avoid these problems, I would like to show this simple example. What you see here is a generation model for getting data. We have here a differential equation with special initial values, and we solve this differential equation numerically, put some random values on it, some noisy data, and then we get this data set. And at this point, we forget everything, how we have got these data. We are looking only for the data. And what we can do, of course, is to analyze this data by graphical method or whatever. But what we want to do is to detect the differential equation which may be behind this data set. Yes, to get this differential equations of the model, we have to generate this matrix C. And of course, we have three data lines, that is X, Y, and Z. So we need at least three equations. And then we have to put in this matrix, these terms, 1, X, Y, Z. But at this point, we don't know whether that is a linear system. Why are they not inside x squared or z to the power of 3 or something like these parameters I've written down here? with x, y, z, we can compute all these parameters listed here, these further nonlinear terms, and can put it in the columns of this matrix C. When you do that, then you can solve the three systems with all these parameters, all these columns in C, but the problem is that our solution vectors, x or xx, xy, xz, are full vector. And that is no information on physics. It says x is a little bit inside, x squared is a little bit inside, x to the power of 3 is a little bit inside. And when we would put in a column with x to the power of 20, then it would say, okay, x to the power of 20 is a little bit inside, so that is no physical information. We cannot use it. What to do? What we have used up to now is that we have used this ordinary least square method. You see in the upper part of the slide, and we get by that always a full vector. And Stephen Brunton, who has built up this method, published an optimized algorithm in his book from 2021, where he used something like a regularization to this ordinary least square method. This is a Lagrangian method where this Lagrangian multiplier depends anywhere on the, let me say, condition of the matrix C we have here. And what you get with that is really astonishing. You get a really scarce vector. Let us see what would happen with, or what is happening with our model. When we use this regularization term, you see that these x dot vector, the parameters for x dot, y dot, and z dot, is now a square vector. And when you're looking at that, there are only two entries in the parameters for x dot, and there are only two entries for y dot equation and one entry for the z dot equation. Whether we have asked for these 15 parameters we have seen in the slides before. And when we are putting that in equation, then you see we get the best fitting solution for these data is this differential equation. And now you can look to the generating equation. And you see here that the generating equation have exactly the same shape, exactly the same parameters we have here, whether we have here put on even random noise on that. So this is a very, very fine method just to ask a system, just to ask better the data of the system, whether there is an explanation term, explanation physics inside. And so here we see it is a linear system, which is rather good to explain all that what we have in the system. Please let me conclude this talk. So first, data science and AI starts a revolution in the friction and the brake modeling and description. Data science and AI can analyze nonlinear physics of brakes and can confirm physical hypotheses. You can ask your data set, is there this physical phenomenon inside or not? So physics-informed AI will be the next generation of software tools in the brake industry, and they will come the next years. They just start to come in the brake industry because they are robust with respect to incomplete, incorrect measurement data. It is even possible to detect physical pattern of the measurement device. That's a problem because you never know when you see these measurement data, are the dynamics of this measurement data coming from the machine or coming from the physics of the contact? And you are able to handle uncertainty as lack of physical information and incorrect or incomplete measurement values. Maybe I have the possibility to talk a little bit more in detail on such AIs with a physical backbone model. Thank you very much. It was a pleasure for me to give this talk. Hopefully we see us soon again. Thank you.